The 7 Series DPO is a performance oscilloscope, perfect for high-energy physics single-shot applications, capturing wideband RF signals, or validating and debugging designs with multi-gigahertz clocks and data rates. It's ideal for looking at signals like DDR4 and 5, USB 4 version 1 and version 2, and PCI Express Gen 1 through Gen 4. The 7 Series offers exceptional features that will accelerate your development by delivering impactful performance and extending the margins to test your products. Gain insights faster with the 7 Series DPO's advanced architecture that moves data within and off the platform faster than ever before. And the award-winning user interface enables efficient analysis with a minimal learning curve. Available in 6 bandwidth options, ranging from 8 GHz to 25 GHz, with a maximum sample rate of 125 gigasamples per second and a standard record length of 500 megasamples, with options for 1 and 2 gigasamples per channel. Both bandwidth and record length can be upgraded remotely in your lab, saving time and eliminating the hassle of sending the scope in. The 15.6-inch high-definition pinch zoom swipe touchscreen and the award-winning intuitive user interface makes the 7 Series DPO a joy to use. Directly position and scale waveforms instantly. Here we have 2 waveforms, which are a differential pair of a 16 gigabit per second PRBS9 data signal. Notice the large waveform view with the ability to stack the waveforms in their own slices. The stack display mode helps you get the most out of the newly developed custom 10-bit analog-to-digital converters by allocating separate full-resolution graticules for each waveform. Each graticule represents the full dynamic range of the ADC while maintaining the often preferred view where the waveforms are separated and easily compared. Of course, it's very easy to overlay the waveforms on screen for comparison if desired. Exploring long acquisitions, millions or billions of sample in duration, is made easy by navigating through your deep record to quickly move to areas of interest. You can simply zoom in on the waveform with the integrated wave inspector controls. Then either use the spring-loaded panning control of the wave inspector, or grab the zoom window and move it out forward or backward in the record quickly and easily. Another very common use case is creating a math waveform from 2 sides of a differential signal when you may not have access to a differential probe. To do that, I can simply touch the Add New Math button, and then at the bottom of the configuration menu, I can select Channel 1 minus Channel 3, resulting in a new Math 1 waveform that represents the differential signal from the 2 sides of the pair. We've even made turning channels or measurements off in the UI familiar, and kind of fun. A practical way to demonstrate the innovation of the 7 Series DPO, especially in our effective number of bits and the resulting signal-to-noise ratio, is to visually show the performance of the new signal path. To do this, I will use a sine wave that has been averaged 10,000 times to remove most of the random noise. We will call this an ideal signal. This is the gray Ref1 waveform at the top of the display. I'll use this nearly noiseless signal to compare the performance of 2 different oscilloscopes. I have previously captured the blue Ref2 sine wave, shown on the bottom of the display, as the single-shot acquisition using a 25 GHz 8-bit oscilloscope. I have previously defined Math2 to be the ideal minus Ref2, resulting in a residual or difference waveform from the 8-bit scope, indicated by the green Math2 waveform on the bottom of the display. In a perfectly noiseless system, this would be a flat line. Now let's acquire a single shot on channel 1 of the 7 Series DPO. Performing the same calculation as before results in a residual or difference waveform from the 7 Series DPO, shown here as the orange Math 1 waveform in the middle of the display. It is very easy to see that this results in a substantially smaller deviation from the ideal waveform compared to the 8-bit oscilloscope, showing the superior performance of the new front-end design of the 7 Series DPO. easily add measurements by selecting from a comprehensive list in familiar categories like amplitude, time, jitter, or technology standard specific. You can see that the new measurements have been added to the results bar to the right of the waveform view. Just like with most readouts in the user interface, when you double tap, you open a configuration menu for the measurement. Here you can do things like turn on statistics for measurements, enable different plots of the dataset, and configure items like gating, which can be global or local to a specific measurement. If you'd rather see the measurement results in a tabular view, you can. Simply add a measurement results table here in the Add New section. Engineers really appreciate this detailed view of measurement results. The flexible windows in the UI allow you to configure the display in virtually any way you desire. Simply grab the top of the view window and move it to a new location, using the blue shadowing as a guide. Notice in the results table on the left, there are results from the current acquisition, and on the right are results from the total population since the last clearing of results. Let's now quickly navigate to areas of interest by using the search navigation buttons in any measurement badge. I'll start by removing the measurement results table and zoom in. Next, I will single tap a measurement badge. Now select left or right arrow buttons to navigate to the previous or next measurement in the acquisition. Do the same for quickly moving to the minimum and maximum values in the record, allowing the scope to do the hard work of searching through the measurement data for you. Once you find the maximum value, you might want to add a label for documentation purposes. I'll add a callout and label this as the maximum pulse width. I can even change the color to match the channel color. Another common use case is needing to gate a specific measurement independently from all other measurements. You can do this easily on the 7 Series DPO by double tapping a measurement badge and opening the gating panel in the configuration menu. Here you can dictate whether you want this measurement to use global or local gating. If we change this to local, we can use one of the numerous methods of gating. I'll select time and set my cursors on either side of the pulse I'd like to measure. Now this specific measurement will be gated by these cursors. Now let's say I want to find all of the positive pulse widths that are greater than 480 picoseconds in duration. I can simply select Add New Search and define the positive pulse width search type, and set the value to greater than 480 picoseconds. You can now see a pink triangular marker in the waveform view, indicating where in the record the search results are. I can now single tap the positive pulse width search badge and navigate to the previous, next, or minimum and maximum values in the record. In high-speed serial standards validation, conducting jitter measurements to understand potential sources of jitter, also called jitter decomposition, is essential. A couple of very common jitter measurements are included standard on all 7 Series DPOs. TIE, or time interval error, which is also used as a basis for drawing eye diagrams and phase noise measurements. Many more jitter-specific measurements can be enabled with optional Advanced Jitter Analysis, option DJA, for conducting more advanced jitter decomposition measurements and plots. Here we have a 16 gigabits per second PRBS 9 going through a 5-inch PCB trace and into channel 1 of the oscilloscope. We can add a jitter summary measurement on channel 1. The jitter summary measurement is a collection of common jitter measurement values as well as an eye diagram, a bathtub curve, and a TIE histogram and spectrum. Because you may want to compare jitter measurement values on two different signals from your system, you can easily add another jitter summary measurement by going through the same simple process, only this time we'll enable a measurement on channel 3. You can now see we've got full jitter summary measurements and plots on two separate signals in the display, allowing you to compare the results directly. You can easily rearrange the windows to your liking by dragging the header of a window to a new location and dropping it where you desire. Another way to analyze this data is in a tabular view. Here you can see measurement results from the current acquisition on the left side of the table, as well as statistical information from multiple acquisitions across a large population on the right. This view of measurement data makes comparing and documenting values easy. With high sample rates and large record lengths, modern oscilloscopes can produce multiple gigabytes of waveform data in just a fraction of a second. In many applications, getting this data off the instrument quickly is very important. While Ethernet has a very large speed advantage over older interfaces like GPIB, the overhead of Skippy commands and the VIXI11 protocol has prevented instruments from being able to fully realize Ethernet's full potential. To take advantage of the speed of Ethernet, we developed Tektronix High-Speed Interface, or TekHSI. TekHSI is based on gRPC and protocol buffers to quickly and efficiently serialize waveform data produced by the oscilloscope and transmitted over Ethernet. The 7 Series DPO features a TekHSI server built in, allowing client applications to connect and receive waveform data from the oscilloscope. The data is automatically pushed to connected clients immediately after it is acquired, ensuring prompt data transfer with no waveform missed, no matter how fast the acquisition rate. Multiple channels worth of data can be moved all at once, ensuring that all waveforms are from the same acquisition. With TekHSI and the 10 gigabit per second Ethernet interface on the 7 Series DPO, waveform data can be moved off the scope at rates of up to 1 gigabyte per second. To demonstrate this capability, I have written a Python script that connects to the TekHSI server as a remote client and simply receives waveform data after each new acquisition is completed, and then writes it to the disk. To maximize throughput and keep up with the stream of incoming waveforms, the script receives the waveform data on one thread and writes it to disk using multiple writer threads. By making use of a Tektronix-supplied library that includes the Tektronix.wfm file format, this script writes the data to disk in the native TeK file format. This library can be included in your own Python scripts so that you can save and recall data in .wfm file format or in CSV.
Also included with the TekHSI package, the TM data types library can convert .wfm files to CSV files or vice versa, with only a few lines of code.
First, I'm going to enable the TekHSI server on the instrument by navigating to the Utility I/O configuration menu. Inside the high-speed interface panel, I'll choose SFP Plus from the network connection dropdown so that I can utilize the port to achieve a much faster data rate. The SFP Plus port is capable of up to 10 gigabit per second data rates and can be configured in multiple ways. Fiber optic SFP Plus modules can be used for longer reaches or when electrical isolation between the instrument and the system controller is required. For many existing installations, SFP Plus to RJ45 modules can be used to run 10 gigabit over existing Cat5e or higher twisted pair cables. For shorter reaches under 5 meters, inexpensive direct attach cables can be used to directly connect to other network equipment with SFP Plus ports. Finally, I will enable the TekHSI server by simply turning it on. With the TekHSI server now enabled, it can accept connections from remote clients and will push data to any connected clients whenever new data is available, without having to query the instrument. I'm going to run my Python script, which will wait for new waveform data coming from the 7 Series DPO, and will simply save the file to a specific drive location. Pressing the single button on the 7 Series DPO will acquire an acquisition. You can see the file quickly show up on the computer's file browser. Pressing the single button again shows another file being saved, indicating no need to query the oscilloscope for the next waveform file. The oscilloscope pushed the data to every connected client via the TekHSI server. I don't want to keep pressing single on the oscilloscope. Instead, I want the flow of data to be real-time as soon as a new waveform is available. So I'm going to press the Run button to start continuous acquisition of waveforms and send each new waveform to the client PC for archiving, which this new transfer protocol can do. So let's go ahead and press Run. Wow, look at how quickly this file browser is filling up with new waveform files. To show that we have complete waveforms, I can open one of the waveform files in TekScope PC, our off-scope version of the oscilloscope application. You can see the sine wave from the instrument here. Take advantage of this free TekHSI capability along with a 10 Gbps SFP Ethernet port to move data faster than ever before. The 7 Series DPO is designed to grow with your needs. Buy what you need today and add capabilities as your applications evolve. Some of the key upgrade options available include optional Windows operating system, arbitrary function generator for quickly outputting standard and custom waveforms, protocol trigger, decode, and search to help pinpoint complex issues during debugging, advanced jitter analysis to measure timing variations and ensure high signal integrity and precise timing, and serial standard compliance testing packages for validating against common serial data protocols. Our engineers continue to add new features and options regularly. In fact, enhancements are typically released on a quarterly basis to help keep your testing efficient and effective. With its low noise, high throughput, and intuitive user interface, this oscilloscope will be a valuable and productive tool for years to come.